What? You can, oh no, I guess I have to introduce Jim if we're going to split this in half. I was going to let you take control with Jim's talk. That's okay, I'll take care of it. All right, so is everybody set? All right, so what we're going to do is we have 15 minutes for this first talk. I'll give Ross a 5 minute when he has 5 minutes. I might give him 2 when he's about ready to be pulled off the stage, but please, speakers, if you could allow a few moments for questions, that would be great. If you do have a question for the speakers, we ask that you go to the microphone in the center aisle. Remember, this is being broadcast, and so it's courteous to let the people listening online to actually hear the questions. Yeah, so let's go ahead and go on. Our first speaker in this afternoon's session is Ross Potter, who is going to be speaking about numerically modeling mega-scale lunar impact basins. Ross.
Thanks, David. So yes, I'll be talking about numerically modeling mega-scale lunar impact basins. When we look up in the night sky and look at the moon, it's very obvious that the moon has undergone intense bombardment over its history with craters of varying sizes. If we look in more detail at the lunar surface, we can see that the moon is covered in roughly 40 to 50 lunar basins. These are impact craters greater than 300 kilometers in diameter. The largest definitive basin on the moon is the South Pole Aitken Basin, which is highlighted by the red line here, which is located on the far side of the moon, and it's approximately 2,500 kilometers in diameter. And that's, to give you an idea of the scale, that's approximately the distance from New York to Denver. So it's a sizable feature. Another feature on the lunar surface that has been purported as possibly being the site of another possibly basin-forming impact is the Procellarum region on the lunar near side. And I will talk through some of the reasons behind this. One of the primary reasons being that it's an area of low topography, as can be seen here in this image. The Procellarum region is also the focal point of a concentration of radioactive heat-producing elements. These are known as the creep elements, so these include potassium, the rare earth elements, and phosphorus. And this particular figure here is showing the distribution of thorium within the moon. And as you can see, there's a very high concentration beneath the Procellarum region. The Procellarum region has been looked at in detail previously. The first major study was undertaken by Cadogan, who, looking at topographic features around the edge of this region, mapped out a basin that was 2,400 kilometers in diameter and named it the Gargantuan Basin. So this feature was similar in size to the South Pole Aitken Basin. A few years later, Whittaker, who wasn't fully happy with Cadogan's study, decided to do one of their own, and in the end came up with an even larger basin, which was 3,200 kilometers diameter, which he named the Procellarum Basin. And again, the evidence for this basin was based on the topographical evidence, so partly concentric ring structures around the edge of this region, as well as it being a general topographic lobe. The distribution of the heat-producing elements, as I mentioned, and also features at the antipode of the Procellarum region, which showed areas of strong magnetic field, which could possibly have been due to a large impact. Due to the more recent increase in the availability of data at the moon, especially the Grail gravity data, the Procellarum region has been able to be looked at in greater detail. So here on the right-hand side is showing a figure looking at the gravity gradient produced from the Grail data, again looking at the Procellarum region. And based on this work, the Procellarum region was thought to instead have been possibly formed as a tectonic rifting structure. And this is highlighted by the blue features in the gravity gradient, this polygonal structure here, outlining the Procellarum region. Now, one of the reasons where the Andrews-Hanna paper decided that the Procellarum region may not be the site of the impact was that it lacks the gravitational signatures that were seen in other basins on the moon. So, for example, in the figure on the right, the other lunar basins can be easily pointed out. with these areas of gravity lows surrounded by gravity highs, whereas in the Procellarum region, you are not seeing the same gravity signatures. However, the Procellarum region cannot be completely ruled out as being the site of an ancient impact. And it's also likely that the moon itself would have been impacted by very large objects early on in its history. And we can look at this by looking previously at the South Lake Basin, which David talked about in the introductory talk prior to this. The South Lake Basin is thought to be 4.3 billion years old and formed by an impactor roughly 170 kilometers in diameter. The Procellarum region is likely to be older than SPA, and impactors greater than 200 kilometers are likely to have been present prior to the formation of SPA, and therefore there would have been some probability of these large impactors hitting the moon very early on. So the aim of this work was therefore to investigate Procellarum-sized impact basin formation on the moon and to see what effects this would have on the lunar surface and interior. There were a couple of ways of investigating large-scale impacts. One of them would be doing experiments in the laboratory. However, the size and scale of impactors that you can use in the laboratory limits the amount of possibilities that you can look at. For example, in the laboratory, you're unable to fully model fully look at the whole-scale melting of rock, which is very important in these large-scale impacts. So therefore, the approach I took was the numerical modeling approach, where you're able to model a variety of impacts at a variety of scales. So in this case, the very large basin-forming events. The specific code I used to do my numerical modeling was the iCell shock physics code, which has evolved over time from a code that was originally developed at the Los Alamos National Laboratory. And iCell over the years has been updated to specifically model impact cratering events, and has been used to look at a variety of impact structures throughout the solar system. So this includes Chicxulub impact on Earth, Hellas-sized impacts onto Mars, impacts onto the outer objects as well, so here including Ganymede, and impacts between planetesimals themselves. This figure here is showing my target setup for looking at these Procellarum-sized impacts onto the moon. So here we have the moon modeled as a fully spherical planet, separated into a Gaborican orthosite crust on top of a dunite mantle with an iron core at the center, and also using dunite to represent the impactor. We looked at impactor sizes above 200 kilometers in diameter and impact velocities of between 10 and 20 kilometers a second, which are typical for this early period in lunar history. Another important parameter to consider is the initial internal temperature of the moon at this time. So this impact is likely to be very young. The moon is likely to also be very hot. And therefore, as a starting condition for the internal temperature, we took our results from our 2012 paper modeling the South Lake Basin and used that best fit target thermal profile as our starting condition for these earlier larger impacts. So the thermal profile we therefore used is highlighted by this red line here, which is equivalent to a target thermal gradient of 50 kelvins per kilometer. As a consequence of using these very hot, high gradient targets, thermal gradients, the internal structure of the moon can be significantly weak. So for example here, within the upper mantle of the moon is essentially strengthless due to the temperatures being at or close to the solidus of the mantle itself. Okay, so this will be a video which can be played in a minute. And what you will see here is on the right-hand side is illustrating material. So again, we have the crust, mantle, and core. And on the left is showing pressure, where blues are lows and reds are highs. When the video is played, you'll see initially a large transient cavity will open up. This will then collapse, forming a large central uplift, which will rise above the target surface and then eventually collapse back down into the target. So if you could play the video, please. Could you maybe go back a slide and see if that will work again? Okay, well, what you would have seen is a similar situation to what David showed in his previous talk. So you would have seen on impact a large transit crater would have opened up, which would result in a shock wave that would pass through the moon, shocking it to high pressures. A large transient crater would form here, which would then collapse, and you'd end up with a large central uplift, which would rise a large distance above the pre-impact target surface. Now, in the numerical models, this is accentuated by the two-dimensional nature of the hydrocode. So along this axis of symmetry here, you end up, because of the conservation of mass, with this a large central overshoot will overshoot far higher than you would expect naturally. And this is probably overestimated by maybe 2 to 4 times what would be more realistic. At the end of the basin forming process, what you see is that you remove a large portion of crustal material from around the basin center, ending up with a large pool of molten mantle material around the center, with crustal material towards the edge. If we move on to the next slide, we can see some before and after views of the impact. So here, this is showing temperature before and after. So we have the before picture on the left and the after picture on the right. And as you can see, during the site, during where the impact has occurred, you've heated mantle material to above a liquidus temperature, creating a large volume of molten mantle material at the center of the impact. You can also see that crustal material has been removed, resulting in a large portion of the lunar surface now being mantle material, and the crustal material has been thinned out to a significant distance away from the site of the impact. So yeah, we can see that the temperatures within the moon have been highly affected here, and even on the antipodal side, temperatures here have been increased to close to the solidus temperature of the mantle as well. We're also interested in how the internal structure of the moon has been affected by these large impacts. And one parameter we can look at is damage, which essentially looks at how fractured the material is. And as you can see here, again, we have a before picture on the left and an after picture on the right. And as you can see here, the damage is essentially saturated at 1, showing that the moon is being completely damaged by this impact. But due to the saturation, this isn't a very good parameter to look at. So another parameter that we can instead look at to infer the internal damage undergone during the impact is looking at the strain rate. So again, we have a before shot on the left showing the conditions before the impact, and the right-hand side showing the after impact. And as we can see, the strain rate the moon has been significantly strained. Again, around the side of the impact, we're seeing the highest levels of strain rate. And this occurs all the way through down the moon, even some high strain rates also occurring within the core. And again, even at the antipodal side, again, we're seeing a large strain rates occurring. So what did these impacts tell us about very large impacts going on in the early moon? Well, they dramatically affect the lunar surface and the interior. We see the removal of crustal material from around the impact site, resulting in the exposure and excavation of mantle material across a large area around the initial site of the impact. The impact also produces a large amount of melt, which occurs over a large area and great depth also. And because of the enormity of the impact, there is substantial damage within the moon, both on the impact hemispheres and also on the antipodal hemispheres. And finally, the intense deformation that has occurred due to these impacts may also affect the formation and structure of younger basins. So this could possibly even include the South Polacan Basin event and also the younger events such as Imbrium and Orientale. And with that, I will conclude and take any questions. Thank you.
Okay, floor is open for questions and discussion. Please go to the mic if you have anything. Yes, this is it. Justin?
Yes.
Okay.
Hey, so interesting talk. So I was wondering, can you, in your model or in, can you envision your model coming up with sort of an estimate of the lithologies, the igneous lithologies it would produce for various sized impacts, based on some assumptions, of course?
So yeah, one thing you can do is look at the composite. So the large volume of melt that is produced will be a mixture of mantle and crustal material, and from that you can not specifically with these models, but others such as Deborah Hurwitz have looked at taking the numerical model results and putting them into looking at how that material will evolve over time and whether that will differentiate to see what kind of lithologies you would ultimately end up creating and sort of forming towards the surface.
Because it would be a logical connection to the flows that you might see in those basins to test the idea. Thanks.
Very quickly, then we have to move on.
Okay, I was just Andrew Jones, PSI at Goddard, and I was curious why you were showing strain rate on your chart as opposed to like average strain or maximum strain, or I didn't understand the time component of that, which was suggested by rate.
Right. Yes. So using strain rates is a good way to look at the Well, so it was looking at the accumulated plastic strain rates, which is a good analogy really to how deformed the material is in terms of the structure of the material within the planet. And strain rate has also been used before to look at impacts on a far smaller scale as well, possibly to infer faulting or other deformational structures. So it's a parameter that has been used previously as well to kind of look at the internal structures of, that are created by the impacts.
Okay, thank you. Let's now go on to the second talk. This will be